say, oops. All right, Mitchell, and I don't know if Darcy and Lewis are watching. We'll be there in just a second. We're going over a couple of things with the binder so they can hear me. Okay, so yeah, it's probably closed. The way that Teacher Ease works, oh, I know I can't till I share, but you're in my way, is I set a time for each assignment. Like I tell it when it's due,
Right.
and I tell it when it's
Close it.
yeah, when it closes. And the thing that can happen is if something happens and I need to reassign it,
Yeah.
I will, it's called force hand in. So it forces the assignment into me and then I reassign it. And you should see it, like you should get a notification that it's been reassigned.
Okay.
So that you know that that's what you're doing that week or whatever.
So what's the easiest screen for me to look at?
You know, I
here?
think a lot of them look here,
Like
but
upcoming.
yeah, I would go with that one or click that assignments button over there. But I think a lot of that one is kind of upcoming stuff too. See, my screen looks very different, but this kind of tells you like what's coming up or what you haven't done yet, what's incomplete. So it's all there, whatever is incomplete. And some of it I haven't graded yet, like obviously your lesson 3, if you didn't, homework binder work, if you didn't put anything in, then, you know.
Okay.
So that's how that works. And there was no homework for 3, so you should be able to see it.
Lesson 2, though, if we didn't have all this stuff, how did we do this?
He participated, he answered questions, even if he wasn't sure what the answers were, which is good. And let me share my screen before I forget what I'm doing. So yeah, so he participated, so that's a good thing, and that's always helpful.
Yeah.
And then so I would give him credit for binder work if he's participating. And I knew you guys were still kind of fumbling, so I wasn't going to be picky and be like, I don't see what you're doing. And then as far as like the homework and stuff went, if I needed to go in and like, it'll show you if I turn something
Yeah,
in.
it'll say like 100 out of 100, 5 out of 5.
Yeah.
Oh.
So these labs we did in class. So yeah, 2 out of 5. So that one I think was, part of it was done, but there was probably like a question that didn't get answered or something.
Okay.
Something minor.
Okay.
Yeah. But if you want to stick around for class, I'll pay special attention to like where we are in the binder as we go through, and hopefully that will help you, give you some idea, or you can split whatever works for you.
I might hang out and
Here,
have
there's
some-
where we are today. Do you have your pencil in the front pocket still, or do you need one?
I think it's in the orange thing.
In the orange thing. Okay. So I'm gonna sit over. Is this okay if I sit right over here so I can put my butt on something other than the floor? Is that cool? All right. I'm just gonna sit here because it's just us today because there's no Mitchell. So
And then I was wondering last week when I was sitting out in the car if I got all the times right.
he's fine.
Freaking out.
Yeah.
I was like, oh my gosh.
No,
I
he's
thought
good.
it said 10 o'clock.
It is for him.
There was one
There's-
group of kids that came in and then 10:30 and I was like,
They're Spanish. So the Spanish kids for Jackie there come at 9:30.
okay.
And then the 10:30 crew you saw coming in, that's my upper class that's starting lab at 10:45.
Okay.
And they get here early and chitty chat.
Panicking.
No, you're fine.
Oh no. I
You
don't
are
want to-
absolutely fine. So I'm not going to do any video of the room or of me because there's no point. So we're just going to go through this. So do you see where lesson 3 is? Oh, do you need a pencil? I've got some right here.
And there. Put the other one in there.
No, I took that one out.
Let's do
Oh,
this
okay.
one.
But the other one that was already
This
in
is
there,
this.
I
This
think
isn't even mine.
it's in your old card.
Oh, here you go. Is blue cool with you? All right, can you find 3 again? Do you need me to find it for you?
Oh, yeah.
And I have some of these little, I don't know why you didn't get one. I do have some of those little things that you stick in.
The little
here.
tabs.
Yeah,
you know
the-
where the- yeah.
Well, it's a big plastic thing that you use to turn the page. It's, they're, here's one. They're like, it's like a big, this guy right here. One of these.
Oh, okay. Yeah.
And those help. I've got them somewhere. I'll get one for you if I can remember it, Kat. So we're in lesson 3. Do you see lesson 3? So we're talking about this week, we're talking about matter and change. And that's because we're about to get into stuff like what the earth is made of. So I think a week ago, I was asking what a certain word meant, and you said, I don't know a lot of words, but I think you know more words than you think you do. So you're honest.
Do.
Yeah. So something to note is I do use a lot of big words. And so if there's something you don't know, you just go, Miss Annie, I don't know what that means. And I'll tell you. So, and April, if you want to like sit crissy-cross on that couch, you're welcome to. That's how I sit. It's
Okay.
deep there because it's supposed to, they call it a cuddler. That corner.
I see.
Mm-hmm. I really like it. And I just sit crissy-cross there with my, dog's ball. Yeah. Yeah, that's a good pen. You're welcome to keep it. Mm-hmm.
I'm just gonna do this.
Oh, you're good. You're good. Yeah, I only cover it because there's a little worn spot there. And you know why it's there? Because I sit crissy-cross and then I do this with my foot the whole time. And I literally rubbed a hole in my, and I can't get anybody to fix it. They discontinued this fabric.
Oh.
Isn't that nice? And I can't find anybody. I said to them, look, you can cut a piece off the back over here. Nobody will see. You can cut a piece off the bottom of one of these. Nobody will, we don't know what to do. So trying to figure it out. And I can't flip it because it's a weird shape.
Yeah.
Geometry, man. All right. So we're talking about matter and change. Okay. And that's because we're going to start talking about what things are made of and how they change because the earth is constantly changing, right? So, I mean, even as you'll see next week, we go down to the river and we're going to look along and look for rocks. And I promise you, if you go down a week later, it's going to look different because the river is constantly moving and it shapes the earth as it goes. And there's forces that cause that. And those forces are acting on matter, which is what stuff is made of. And we're going to get to that in just a minute. Now, I apologize for weirdness on the screen. Jason got a new media center. He got a new router. We lost internet for almost a day. And there's something strange about my connection. And those are not normally there. They'll be gone next week. He was up last night till like 1 a.m. trying to fix them. So let's see what we're doing. So matter and change. So what's matter? Have you ever, not what is the matter, but what's the matter, right? So do you know what matter is?
Yeah.
What is it?
It's something that has weight or can take space.
Oh, that's so good. I'm going to get my coins out over here and I don't need to put my mat out because you're the only one here. Yep. The only difference only change I would make to your statement is instead of weight, we say mass. And I'll tell you why. Because weight is like, okay, say this weighs a pound. Okay. What weight is, it's the effect of gravity on the mass, on the matter here, the effect of gravity on the matter. So mass is like how much of something there is. And then weight is gravity acting on it. And so here's the thing. So if this weighs a pound right here on Earth, if I took it to the moon, is there going to be less of it or is it going to be the same amount? Well, it'll actually be the same amount, but it will weigh less because there's less gravity on the moon. There's less effective gravity. So have you seen pictures of astronauts floating inside of spacecraft? Have you seen that before? Yeah, exactly. So there's not less astronaut when they get in space. Like they go up there and they're the same people. They didn't lose any of themselves, but they weigh less because there's less effective gravity. So matter, as you said, is anything that has mass and takes up space. And we can also say that the amount of matter within a given space, we can also call that volume. And that would be like, this is I think it's a half a pint jar. So I could put half a pint of liquid in here. That's imperial. We don't use that in science. We use liters and milliliters and things. We try not to use things like pint, but that's how it's bought at the store because we're America and we don't want to change. So all matter is made up of atoms. So have you heard of atoms before?
I know we're made of it, but I don't know what it is.
Okay, so if you look up here on the screen, do you see this image right here? So this is a diagram of an atom, and the first thing I'll tell you is it's really hard to diagram an atom. And we really don't have a good way to do it. We've tried, and we have these models you can put together, and they're kind of crazy, but none of it is really accurate. So it's this kind of a concept. Do you know what that means? Like a concept is kind of like a thought. So the way atoms work is at the center, okay, this part in the center, we call this the nucleus, okay? And in the nucleus, there are two kinds of particles. So we have, see the ones with the plus? And then you see the ones that don't have a sign. The green ones have no sign. And see the green ones over here, it tells you what they're called. Those are called neutrons. And then the protons are the positive ones. So what this means by a charge is, you know, when you put a battery in a toy, there's a plus and a minus end, and you have to line it up correctly. Like if you put the negative in where the positive in, it doesn't work, right? So this all has to do with electricity and electric charge. And in chemistry, in like 2 more years, if we get to chemistry, if you're still with me then, We'll talk about it a lot, and even in physical science, which is next year. And that's because the reason that electricity works is because of these little dudes right here. Okay, these are the next ones. These are electrons. Okay, and they have a negative charge. So you have a positive charge and a negative charge. But here's why we can't really diagram them well. First off, the middle here, where your protons and your neutrons are, these guys, these protons, they don't have much mass. They don't weigh a lot. There's not much to them. But the neutrons actually have more mass. So they actually have some weight, sort of. Like if you were to say, how heavy is this atom? Yeah, it's okay. Nope, it's yours, I think, because mine's being still. And then these guys here, these electrons that they fly around the outside of the nucleus. They don't have much mass either. So really the only thing in the atom that has a lot of mass, Cal, are the neutrons. Now, these guys right here, here's why we can't like really show what they look like. Do you see how it's got these electrons over here in these little circles? Okay, so here's what you have to imagine. So you have neutrons and protons, and they're all kind of packed together in the middle, like a little ball, all right? And the electrons are flying around it, but they don't fly around like planets go around the sun. They don't have an orbit that goes like this in a circle. They go everywhere, but they stay within a certain level. Some of them only fly, like if this is the center of my atom, some of them will only fly this far from the center, but they'll fly in all directions. And others will fly this far from the center, but they'll fly like in a figure 8. And then others, it's kind of crazy. So we really can't see it. So we draw it out like this because it helps you understand how many there are. And so we talk about, how do we put matter together? How do we combine things? Because we obviously have things that are elements, which we're going to talk about, and then we have compounds and mixtures. So here's what elements are. So an element has only one type of atom. So for example, this isn't true anymore, but what's this one? What is that? What coin is that? Oh, it's the brown one. Yeah, what coin's the brown one with Lincoln on it? That's a penny, right? Do you know what color is on the outside of a penny? Do you know what metal that is that you're seeing? Yeah, very good. So it's copper. So copper is actually really expensive right now. And that has to do with, just supply and demand. We have to get it out of the ground. We mine copper. Interestingly, you'll learn next week, we mine a lot of metals, right? We pull them out of the ground. Copper is one of the only ones that isn't mixed in with something else. It runs all by itself in these big veins or lines underground. It's pretty cool. So copper is expensive. Pennies used to be made of solid copper all the way through. Now they're just coated in copper and they have nickel in the middle. But if we can pretend this is an old one, like a 50-year-old penny, it would be copper all the way through and nothing else. So that's what we call like an element. It's all just copper. There's nothing else there. So a compound is going to be, come on, crazy TV. Oh, we'll get to that in a second. Okay, here's what we do: symbols for our elements. So this thing right here, have you ever seen this before? Okay, so that's a periodic table. And when we get to chemistry, it's really involved, but it's a little involved in earth science. This is basically how we organize elements so that we can understand them. And we can use them in labs, and we can figure out how to use them in industry, because this little table actually gives us a lot of information. And there was this dude named Mendeleev who developed this cool Russian scientist. And it's funny because I've never seen a picture of him where he looks happy. He looks mad in every picture. He looks scary, like for real. If you look at pictures, have you ever looked at pictures of Mendeleev? He looks terrifying. Like, that was part of my joke when I was teaching that lesson. I'd put up a picture of him and I'd be like, does he look like somebody you want to meet in an alley? Like, no, he's a scary looking dude.
We used to have a dog named Nana.
Nana?
We had to put her down because she was in bad pain.
Oh, that's
Every
terrible.
single time she would look sad.
Oh, that's awful. She looks sad all the time, but she was trying to tell you something about how she felt. I think Mendeleev just looked mean. I just think he knew how to smile. But anyway, he's a very cool guy. I don't know. Probably not. It could be my mother's dog. downstairs bonking on something. I'm not sure. So anyway, we put we put our elements in this thing called the periodic table. And if I zoom in on it a little bit, if it'll let me, there you go. You can see that there's lots of different letters here, right? And there's little numbers beside them. Well, that's up here at the top. So this one is hydrogen. This is how we put hydrogen in the periodic table. And it's going to be right here. And it has a number 1. Okay. And the reason it has a number 1 is because this has to do with how many protons it has. So only one of those plus particles, right? And then we give it a mass, and this is basically how many neutrons it has, which are the ones that have, remember, they're the ones that have mass, the others don't really have mass. And then we give it a symbol and we give it a name. So you don't have to memorize any of this or anything, but you kind of just need to be familiar with the fact that it exists because it's going to show up from time to time. So if we talk about elements, so things that are not combined, just pure elements, like the things that are on the table, do you want to guess? Do you know what abundant means, first of all? Okay, so abundant means like how often you see something. Like I find deer to be rather abundant in this neighborhood. I see them all the time. I actually worry because I see so many of them, right? And I could say that that awful nutsedge weed is quite abundant in my front yard at the moment. So abundant means there's a lot of something. So do you want to guess what the most abundant elements are in the universe? The whole universe, what would you guess? Trees. So trees are an element. So what we're looking for, this is a good guess though. What we're looking for is hydrogen. Yeah, hydrogen and helium. And let me tell you why. Because at the center of the sun, you have hydrogen and helium, and they're actually next to each other on the periodic table. One has 1 proton and one has 2 protons. And they're like constantly having these little chemical reactions where they're switching place, and it's fusion basically. And that's what's making so much heat. You basically have hydrogens turning into heliums, and it gets really, really hot in that reaction, and light. That's where we get it from. So that's because the sun is so huge. Now, if we talk about Earth, it's going to be oxygen, silicon, and aluminum. Weird, because where do you see aluminum? Like, do you know where you see aluminum in your life? Like, does it sound like anything you've ever heard of before? Yeah, do you wrap stuff up in the kitchen with it? Yeah, aluminum's really flexible, right? You can, and if it's really thin like that, you can use it as foil. Also, you might see it on, I think a lot of the like trailer type things are made of aluminum, like the siding that goes down the truck trailers. And what else is aluminum? There's a lot, cans, soda cans are aluminum. Silicon is something you probably don't see very much because it's inside of rocks, basically. But this is the stuff that makes the clear, glassy things. So like quartz, and if you get quartz sand and grind it down enough, you can make glass when you melt it. That's because of silicon. And it's also in microchips. It's very important in microchips and computers. Silicon Valley is a place in California. Actually, my husband was there last week. And they call it that because that's where all the computer developing is. Like all the fancy stuff is there. Oxygen, you know what that is, right? Yeah. So oxygen's in the air you breathe. And you, as an animal, need to breathe oxygen because your body does what's called cellular respiration. That's how you get energy. Whereas trees do photosynthesis, the opposite of that is cellular respiration. So oxygen's a gas, hydrogen and helium are gases, but silicon and aluminum are solids, okay? So if we talk about compounds, this is when we put 2 of those elements together and they become something completely different. So this one right here where it says, do you see where it says NaCl? Do you put salt on like do you like scrambled eggs? Do you like corn on the cob? No. Do you put salt on anything at the table? Ever? No? Well, if you did, yeah, she salts beforehand. So what that is it's a sodium and a chlorine. And chlorine's actually in pools. You ever been in a pool in that smell? That's chlorine, but that's chlorine on its own. Yep, that's how it works. Yep. So, and the pool's probably not sodium. It's probably, is it like potassium chloride or something that goes in there? Yeah, something like that. Yeah.
I don't know.
There you go. Come on over there. That's good. They don't have to turn your head so much. So this is sodium and that is chloride. And when you put them together, they turn into something completely different and you get table salt, which is important. Now, this one right here, that's iron 2 oxide, and that is actually rust. If you ever see rust, if you take a piece of metal and you leave it outside long enough and oxygen comes in contact with it, you get rust. You get copper oxide. What color is the Statue of Liberty? She's green. Okay, so she's actually made of bronze, which is an alloy. It's when you combine metals, but one of the metals in there is copper. And when copper is left in contact with oxygen for too long, it turns that green color. So when you see the Statue of Liberty, she's not painted. That's a chemical reaction that caused it. And it caused, like that says FeO, that's iron oxide, but there is a copper oxide that forms. And so those are chemical formulas when you see those letters all stuck together like that. And that just shows what compound there is. Now, a molecule is what we call the smallest unit of a compound. So if we were to take table salt, and if you look at it under a microscope, it's like little clear cubes. And if you crush it and keep crushing it and keep crushing it, if you could break it down to the smallest form, you would find just one molecule of sodium and chloride. And if you break it any further than that, you don't have salt anymore. You have sodium and chloride. So this is just the smallest unit, and that's all you need to know, really. So molecules are smallest units, and they typically, when we talk about molecules, we're talking about a type of bond we call covalent bond, and you don't have to worry about that too much. But basically, that means that the 2 elements or 3 elements that are involved, or whatever is involved, that they share electrons. And you don't have to get that concept too much, but if you know, you may hear covalent bonds share electrons, and then they're ionic bonds, and that's when one steals from another. And I have little graphics that actually show little atoms stealing things from other atoms. It's good, helps you remember. So your molecule is a group of 2 or more atoms, and they're held together by bonds. And a compound is a substance which is formed by 2 or more different types of elements, which are chemically in a fixed proportion. That means you can't change the number. Like right in this one right here, it says C6H12O6. So what this means is C is carbon, there's 6 carbons, H is hydrogen, that's 12, there's 12 of the hydrogens, and then there's 6 of the oxygens. This is actually glucose. That's what blood sugar. That's what, the sugar your body makes is this. But if I took that and I was like, C5H7O4, it wouldn't even work, first of all. They wouldn't go together, but you'd not say they're a fixed number anymore. The proportion has changed. Always has to be the same. Can be multiples, but it's the same. So chemical bonds, here are different types. We'll go over them quick because you don't have to understand the concept behind them too much, but know that they're different kinds because they may come up in a lab here or there. You'll see a little of it today, actually. So if you've got 2 atoms, they're attracted and they're sharing. That's when I said a minute ago. Those are covalent. They share electrons. It would be like you and your mom sharing a soda, okay? And when one transfers it to another, that's kind of like where one steals from another. That would be like if you just took your mother's soda and walked off with it and left her sodaless, okay? That would be an ionic bond. It would be very rude, right? And then this one right here, this is polar, and that means they're shared, but the electrons repel each other. And here's the important thing to know about polar bonds. Okay, so you have a molecule and they're sharing electrons, but those electrons, the way they're flying around, you have more protons on one end of the molecule and more electrons on the other end of the molecule. And that causes the molecule to have a charge where one end of it is positive and one end of it is negative. And a great example of a polar molecule is water. Water is polar. And that's important because, like, say you want to wash a greasy dish. Okay, one of the things you use is dish soap. The chemicals in dish soap will actually catch the water and in a way they kind of trap the oil, and they can wash the oil away because it's a surfactant. But it's important that the molecule have the charge because that's how things interact. It's also why electricity can go through water. Because if you think of it like a battery, remember, like you put the positive, you ever done where you stack the battery where you put like positive end, negative end, and then you put another battery right here. You put the negative end to the positive end, another, you ever done that? Where they go in a stack? Sometimes they'll go in a line. And if they're in a line where your positives are always touching your negatives all the way down, negatives are touching your positives, they're all same direction, that's basically, you've made a big polar cell charge. So positive on one and negative on the other. Don't have to worry about it too much yet, though. So then you have hydrogen bonds. That's the kind of bond that's in water. It's hydrogen and polar, interestingly. Hydrogen bonds are easy to break. And then you've got metallic bonds. Hey, so you still got several minutes, Drew, so you're good. So your metallic bonds, these are the ones that are in metals in particular. And the way they're structured, Cal, they allow for really high conductivity. So that means it's very easy for electricity to move through them. So you good, Liam? Cool. You guys still have a few minutes.
I was just looking at her stuff.
Absolutely. You may look, just don't touch it. So we have two different kinds of things called ions, and you don't have to understand what ions are at your level, Cal, but you may hear in lab, and we'll explain it if you do, but you may hear cation and anion. Cation is positive, and the way I remember it is it's positively cutest ion ever because it looks like a little cat. And then the anion is easy to remember because if you remember, he's an onion with a negative attitude or a negative charge. That helps remember what they are. I love. See you later. So chemical reactions. This is when you put two different types of molecules together. They can be elements or compounds or one of each or whatever. And then something happens. They react with each other. And this has to do with how the electrons are interacting. But these are 7 signs of a chemical reaction. So have you ever seen a chemical reaction? I bet you have.
Yes, you have. We've made those volcanoes and when you
Ah.
mix
Baking
things
soda
together,
and
it
vinegar.
makes it explode, right?
That's one. Okay. So what happened there? You did we made bubbles, right? So what are bubbles proof of? Something's happening. What happened? You made a gas, right? You created a gas. A gas came from that interaction. Have you ever put an apple slice out on the table and left it there for a while and come back later and it's a different color? No, you never seen that? They turn brown. Yeah, that's because of the oxygen in the air.
When you've eaten it.
You can take a bite and leave it there and come back and it's brown. Or you leave fruit in a bowl for too long. Like I leave my apples and bananas and things. I usually have a big bowl on the counter when it's not lab. And sometimes they turn brown, like they rot. That's a chemical reaction. So that gives you both a color change and sometimes a smell. So gas, smell, color change. How about those? You ever have those glow sticks at Halloween that you crack and then suddenly there's light? That's chemical reaction. So
Yes,
light.
like you break around a table and shake.
Yeah. So light is another one. How about you ever seen those little cold packs or heat packs where it's like a little package and you break it and shake it and it either gets cold or hot? You ever seen those? So that's another chemical reaction. And if you had your hand in the right place on your volcano, you may have noticed that actually gets a little warm. There's a little heat produced in that reaction. So here are 7 signs, okay? Odor, production of an odor, which some things just smell when they mix together. You can smell when something's rotting, right? You can smell when like a banana's rotten because it's produced a smell. Formation of a precipitate. We're going to come back to that one because that's the hard one to understand. Evolution of a gas. Gas came up. Change in temperature, which we talked about, gets hot or cold, production of light, production of sound. Sometimes you'll hear a pop or something like that. Absorption or release of electrical energy. That's another one. That's like when you're using a battery. That's a chemical reaction. Now this one right here, precipitate. Have you ever heard the word precipitation when they're talking about weather? Yeah. What's it mean, Liam? What's precipitation?
Like condensation or like raining.
It's anything coming from the sky, right? So it could be hail, it can be sleet, it can be freezing rain, it can be rain, snow. That's all precipitation. It's stuff falling out of the sky. A precipitate in a chemical reaction is something that like falls out of the reaction. It's like it creates another little solid, and it's usually a solution, and that solid comes down. I think one of the things today you might get to see a little bit of that in lab. So we'll wrap up with this. We've got a couple more minutes. He's good and doing all right. Do you need a stretch? Are you good? Stretch break? Shake? Sometimes I have to do that. So mixtures and solutions. So let me ask you this. If you were to make a salad, do you like salad? Okay, what would you put in your salad? You like the crunchy things? Which kind? The little noodle ones? Or the croutons? Yeah. I love the little noodles, the little chow mein noodles that are dried. I like croutons too. Actually, I had croutons last night. So is there lettuce in your salad already? Yeah.
You can't have a salad without lettuce.
Lettuce or spinach or something. So you got green stuff of some kind. And then you got croutons. What else would you put in there? No, would you put carrots or salad dressing? So here's the thing. Say you got your salad, you got a bowl full of lettuce, you put in some, let's say you like carrots. You toss in some carrots, you toss in some croutons, and you mix it all up together. Okay. If I said to you, Cal, pour all that out on the table and put all the carrots in one pile, all the lettuce in another pile, all the croutons in another pile. It might take you a while, but could you do it? Yeah, because that is a mixture. So what that is it means everything is together, but nothing is, come on. Ay, there you go. They're not chemically bonded. It's all still the same. Carrots are still carrots, right? Lettuce is still lettuce. Croutons are still croutons. It's the same. You can't take it apart. So a solution is when you can't get it apart. So a good example of that would be like a glass of iced tea. All right. So you take the tea bag and you put it in the, or hot tea. You ever taken a tea bag and put in a cup of water, made hot tea? You ever done that? No. How about hot chocolate? There's one. So you have all those, yeah, there's sugar and cocoa and stuff in there. And if I said to you, after you poured it together and stirred it up, if I said, Cal, pour that out on the table and put all the sugar over here, put all the dried milk over here, put all the cocoa over here, could you do that? Like out of a cup of hot chocolate? No. And a lot of that sugar is going to be dissolved, right? It's not even little granules anymore. It's all dissolved. So that's a solution. That means it is what we call homogeneous or homogeneous, some people say. And that just means that it's all the same all the way across. It looks the same. It doesn't have things that stick out. So it's all the same. And you've got particles that you can't distinguish or tell apart. So in your hot chocolate, you can't tell your sugar from your dried milk. It's all mixed in. It's a solution. There's two things in a solution. There's also different kinds of solutions, which we'll talk about later, but there's two things in a solution. There's something that does the dissolving and something that is dissolved. So if I take a glass of water and I put sugar in it and I stir it up and the sugar disappears, what was dissolved in the glass? The sugar. Okay. And what did the dissolving? What did I put the sugar in? A glass of what? Glass of water. Okay. So if I put sugar in water, then you have one thing that does the dissolving. In that case, it would be the water. And we call that the solvent. And whatever is dissolved, we call the solute. So those are words you might hear. So, ta-da, states of matter. This you probably actually already heard before. This probably is review for you. So we have different states of matter. We have one state of matter. Come on and change. Oh, this thing is so laggy. There we go. We'll have it fixed next week. So we have one kind of matter where we say that its volume stays the same and its shape stays the same no matter what container you put it in. So if I take this penny and this is not American money. If I take this penny and I drop it in a glass, it's still going to be a penny, right? I put it in a cup, or if I put it in a box, it's still going to be a penny. It's still going to be this shape and nothing changes about it, right? So that is what we call a solid. Very good. Yep. And we have different types of a solid. We have ones that we call crystalline and ones we call amorphous. And that has to do, will you please change? There you go. That has to do with the type of molecule that's in them. So crystals are crystalline, right? And then most other stuff, a lot of stuff you see is amorphous. And some of the crystals are so small, you don't see them. Hey, Drew, you guys, okay, be quieter. So you don't see them because they're just kind of part of stuff and they're tiny, they're microscopic. So if I have something that changes shape to fit into a container, but its volume stays the same, do you know what state of matter that might be? What might that be? Changes its shape. Yeah, but its volume stays the same. Bingo, man. Because if I put water in a fish tank, it's going to be the shape of the fish tank. And if I take that whole fish tank and I pour that same amount into my bathtub, it's going to change shape, but it's still the same amount, right? So, okay. What changes shape and volume? Do you know? The other state of matter, the other big one. You got solid, liquid, and through a yawn as you breathe it in. Solid, liquid, and what's the other one? Gas. So gas is going to change its shape and its volume. It's really easy to compress gas. If you blow into a balloon, you're putting that under pressure. So you're taking all that air and you're just kind of compacting it. It's easy to do that with gas. It is more difficult with liquids and much more difficult with solids. Everything can be compressed to a degree, even diamonds, which are really hard. Sooner or later, they're going to crack, but So the last one is plasma, and this is not seen too often on Earth, and it's not something you're going to come in contact with really, but there's a lot of plasma going on in like space and the sun and whatever. So changes of state, I bet you can figure these out, some of these at least. Do you know what it's called when something goes from a liquid to a gas? So this would be like a puddle outside is there one day and then there's sun and now there's no puddle. What happened to it? Do you know? Think about it. What's it called? So that one's evaporation. Okay. So this is what we call it. If you like, if I puddle outside and then a bright sunny day and the puddle didn't disappear, it doesn't go away, it just changes from a liquid to a gas. How about if it goes from a gas to a liquid? That's like if you take your cold drink outside on a humid, warm day and suddenly you've got water all around the outside of your drink. Do you know what that is called? I think you said it earlier today. I think you did. Yeah, that's condensation. So that's what it is when your gas turns to a liquid. It's going to change. There it is. Now, this one's a little harder. Solid to a gas. Have you ever heard of that happening? I'm going to tell you when you can look for it, okay? Every year when it snows, all right? Every year when it snows, and I tell all my kids this all the time, and they know to look for it now. When it snows, there's going to be some nitwit on the internet, and here's what they're going to do. They're going to take a snowball, and they're going to squash it all up in their hands, and then they're going to take their lighter, and they're going to put their lighter to the snowball, and the snowball is going to turn black. Have you seen this before? You ever seen that? Okay, look for it next time it snows. Ask your mom, because somebody on social media will be doing it. You seen this? And they go, oh, the snow isn't real. Look, it's turning black. No, you're getting soot from the lighter. But the reason it's not dripping and becoming liquid is because it got so hot so fast. It's what we call sublimation. It went right from a solid to a liquid and didn't go through, right from a solid to a gas and didn't go through, I can't speak, and didn't go through a liquid phase. It just poof. So that's sublimation. Now, if you go from a solid to a liquid, if you put an ice cube on a table and leave it there, what's that called? I know you know that one. Yeah, you do. What happens to a snowman when it gets warm? What happens? It melts. Yeah. You know it. So melting is when you go from a solid to a liquid. It's also melting when you take metal and heat it up to the point where it becomes liquid. That is also melting. We don't think of it that way, but anytime you take a solid, turn it into a liquid, it's melting. So liquid to a solid, what if you take your orange juice and you put it in a popsicle thing and you stick it in the freezer? And later you get a popsicle. You went from liquid to solid. What's that called?
I've done that
I
before.
love it. What's that called when it goes from a liquid to a solid? You know, I know you know. You put water in the freezer and it freezes. Freezing. There you go. And then this is the last one when it goes from a gas to a solid. And you probably haven't heard this one before, but that's deposition. And that will happen sometimes, but you don't see it very often. There aren't even like great examples because you just don't see it, not too much in your day-to-day life. So last thing we're going to talk about here is conservation, the law of conservation of energy. And I'm actually going to give you a little biography on a super cool scientist who studied this stuff. Okay. So the law of conservation of energy, this is one, I forgot to put my little Rico logo in here. I'm going to have to do that. This is one that you should, I'll do it right now so we don't forget, but this is one that you should never, ever forget. And this is one that should stick with you. I got to put my Rico in. Remember my little Rico that I put in here? When you're supposed to remember something forever? I forgot him. I'm going to have to put him in here real quick. Look at this. See all my files? I have so many files of things. Files inside of files. Play. Where is it? Yes. Files inside of files inside of, there it is right there. Huh. So I got to put him in here because we don't forget him. So, oh, come on over now. So the law of conservation of energy says that energy cannot be taken away from anything. It's never gained or lost. It only changes shape. And that's important because, come on and do your thing. That's important because energy never goes away. It just changes its form or its shape or how you see it. So if you put a battery in a toy, okay, and that toy moves across the table, basically what you've done is you have taken the chemical energy in the battery and changed it into kinetic energy in your toy. It's just a different kind of energy. So energy cannot be created or destroyed, but rather changes form. And that's one to remember forever. Energy can't be created or destroyed, it just changes form. So this is some cool stuff. So concepts behind this law, conservation of energy, they go back a long time, like 1600s at least, people were writing about it. And it kept getting refined or tweaked, made a little better by every single scientist who studied it afterwards. Little better, little better, little better. But one of our most interesting contributors is Émilie du Châtelet. Okay, so a French lady. Okay, and her full name was Gabrielle Émilie Le Tonnelier de Breteuil, Marquise du Châtelet. You want that name? Yeah, yeah. So Emily was born into a wealthy family. And she was what we call a philosopher and a mathematician. And what she's most famous for is she translated a book from Isaac Newton. Have you heard of Isaac Newton? So Isaac Newton is probably one of the most famous scientists of all time. He was really big at physics, basically, physical energy, physical stuff. And he wrote this book with this Latin title, Philosophiae Naturalis Principia Mathematica, or Principia. People still use it today. She translated it from Latin to French, and her translation is still the only one that French people use today. Nobody's done it better. But what she did that was interesting is as she went along, she included some of her own notes about her theories that Newton had developed, and she added something to Newton's theories that Newton had missed. And basically it has to do with kinetic energy of motion, so energy of things in motion, that there's a relationship between the total energy. It's very technical. But she was describing this relationship between mass, like remember that's like how much of something there is, and velocity. Velocity is a movement in a particular direction. Okay. So she talked about a relationship between like a car going down the road. Think about a bus versus a smart car. One of them is going to have going to take more energy to move the bus, right, than it is the smart car. So this kind of stuff she did. She translated this book, but her translation and her theories were not published until after she died. And here's why, because she has a very kind of a sad story here. There's a video, but I'll actually share it. You guys can look at it at home because I'm watching the time. There's 3 minutes left. Actually, I'll play it after I finish this little talk on her. I'll go back and play it. So here's the cool thing about her. This is, well, not cool, interesting. So in 1749, at the age of 42, she was pregnant with her fourth child. Okay, here's the thing about being 42 and pregnant in 1749. It was not very safe. They didn't have good medical care, and that was old. That was considered pretty old, 42. Like if you lived to 42, you're pretty old. People got married at like 16, right? 15. So I remember everything was earlier. So this was when she knew.
It was 41.
There you go.
She was 42 and considered old.
Old, very old. And it was not very safe for her to be having a baby at that point, but too late, she's having a baby. So she really wanted to get this stuff done with Newton's stuff that she was translating. So she basically stuck herself in a room and ate only what servants brought her and worked tirelessly for like weeks, months. Nobody came in. She didn't visit with anybody. She just worked and worked and worked and worked and worked. And she only took little breaks because she just really wanted to get the work done. So she finished her book sometime between September 1st and September 3rd. And her daughter was born on September 4th. And she was actually very good friends with Voltaire, who was a famous French philosopher. And he actually said his little kind of joking, funny quote was, "The little girl, the baby, arrives while her mother was writing at her writing desk, scribbling some Newtonian theories, and the newly born baby was placed temporarily in a quarto volume of geometry while her mother gathered together her papers and was put to bed." Basically, he was just saying she was working until the baby was born. And so 6 days after the baby was born, Emily came down with what they call childbed fever. It was basically an infection that came after having a baby, which was not uncommon back then. Now it's very, very, very rare. And she died within 6 days of that baby being born and just got her work produced. I mean, like just got it produced. And it didn't get published until after she had died. So she never got to see anybody appreciate her work. So here, I'll put that video on and we'll give everybody a few more minutes to show up because they're all coming. I think we have sound, but I'm unsure because everything's weird in here right now. Oh, maybe we don't. Nope, we don't. Okay, hold up. Hold up. Because everything is crazy right now. I know we got the TV hooked up, but I don't think you got sound hooked up for me. And I don't even know how to do it because I'm afraid of this thing.
It's okay.
I'll send you the link. But basically, it just tells you about kind of like her life. But here's the other neat thing about her. So she was born into a family of all brothers. She was the only girl. And back then, like usually the girls, they sent them to a convent to live with nuns and whatnot. And that's kind of where they got educated because girls didn't go to school. But her dad recognized how smart she was. And he was like, no. So they homeschooled her with private tutors back in the 1700s. And by the time she was like 12, she could speak like 11 languages. And she knew all the things that typically only boys knew, which was very special. She was very different in that regard. So she, if you look her up, April, talk about a party girl.
Oh, yeah.
A little more than friends. with
Well,
Voltaire.
I mean, at
Yeah.
42 and pregnant in those days.
Well, and so she had a husband. She was married off, of course,
Yeah.
to this army guy who bored her to tears. So, and he was gone all the time, and they kind of had arrangements.
Yeah.
And Voltaire was part of the arrangement. And so that's why
So
he was even there when her
whose
baby died.
was it?
Not Voltaire's and not her husband's. Yeah, she is a party girl, but she's so cool because she was so different. And actually, the fact that she had somebody to defend her that was so respected, like Voltaire,
Right.
like he actually had to sign on to her work a lot of the time. His name was on it when she did it. Like he admitted many times that she just dictated and he wrote
Yeah.
and put his name on it.
Right.
Because there was no way it would get published otherwise.
Right.
And but it's interesting, like when you compare her and she had somebody like Voltaire backing her up, where at that point, you need like a man in society to
Right.
basically give you some sort of validation.
Right.
And then you compare her to like Rosalind Franklin, who basically discovered the structure of DNA and got thrown under the bus and had literal spies take her work to other people who got the credit.
Mhm.
And nobody said anything about that till after she died. And even till like a couple of years ago, because Francis Crick is still alive and he did a TED Talk. And he even threw her under the bus in the middle of TED Talks. Like, what are you doing? We all know better now. Like, and she went and died of cancer from all the radiation. She got, I think it was uterine cancer, ovarian cancer. And it was like the most ironic. It was like, because you're a woman, all of it was because you're a woman. It was terrible, that woman.
Mhm.
So Cal, here's your money for today. Woo! Did you tell your mom what you do with it? You know what you do with what do you do with money? What's it for?
You told me to buy.
Yeah, the machine at the door.
But
Yeah.
when he told me in the car, when
Yeah.
he freaked out last week, he forgot his money.
It's always going to be here. There's always more money.
Anyways, I saved my money.
Oh, there you go. Well, I have to remember to give you the bigger coins then, because I usually just throw them out. I don't pay any attention to what they are.
He saves them and he wraps all of his coins and,
Do you?
oh yeah.
That takes some effort. All right, I'm gonna end this one. We're good. All right, gang, time for them.